I showed you here a second order system which is given by the block representation here, and I told you that the second order system examples of such systems are mass spring damper and RLC circuit in electrical network. And in general, we write the second order system, we represent them in the form of block representation shown over here. We have parameters A and B. So because this A and B will be decided by what components are present in the system and what system you're dealing with. For example, if you're going to deal with the mechanical system, you'll be having these parameters different. And if you're going to deal with electrical system, again, you'll be having A and B different for electrical networks. So in general, we define this as A equal to omega n square and B equal to zeta omega n, where omega n is the natural frequency of oscillation, while zeta is the damping ratio. So they are new terms, and you will come to know why we are going to have these terms here. And since in the first order system we saw that there is no oscillation that will be present in those systems, so first order system never exhibit oscillations. And second, in second order system, you will see that it has in some stages it will exhibit oscillations, and that is why we have the term omega n. And then again, when you talk about oscillations or motions in second order system, you will have some sort of damping or energy loss because of some other elements. For example, in mechanical system, you try to damp out the oscillations using the dashpot. Then again, in electrical network, you have resistor which acts as a damper or energy dissipator. So in order to understand what omega and zeta are, so if suppose that we talk about this mass spring damper system and you provide a small amount of energy to this, let's say you exerted force to this mass, then what happens is, forget about the dashpot for the time being. If I exert a force on the mass, so what I'm doing is I'm going to provide an energy to this mass. And initially I will, so that depends upon what type of force you're going to give. If you're going to give an impulse input to this mass, for example, the impulse input may be a hammer blow. The example of impulse is a hammer blow. If you're going to give a hammer blow to this mass, then it is going to have kinetic energy stored within it, and will start moving, compress this spring. So we are talking about a system comprising of spring and mass only. So for the time being, forget about the dashpot. So if the system comprises of spring and mass, if you provide some energy to it, so you'll see that during half of the cycle, the energy will be stored in one element in the form of kinetic and mass, and during the next half, you'll see that the energy will be transferred to the spring in the form of potential. And because of this energy exchange between spring and mass, or in other words, the energy that is changing from kinetic to potential and then back to kinetic, will cause oscillation in the systems. And that oscillation will have certain frequency called as natural frequency of oscillation. Now, if you suppose are going to incorporate a damper, an energy dissipator. So in the mechanical system, it's the dashpot, while in electrical system, it's the resistor. So these are energy dissipators. So once you have oscillations within the system, what these energy dissipators will do, they are going to dissipate the energy within the system, and thus what you're trying to do is you're trying to damp out the oscillations. So for this we have the parameter called as zeta, which is damping ratio. So we'll talk about zeta, how do you get this, and we'll do some examples where we'll try to obtain the log representation of the system, and from there we'll conclude what zeta and omega n in terms of mass, spring and dashpot parameters come out, or in terms of RLC, what these values, these parameters look like. So dashpot and resistor are going to dissipate energy and will damp out the oscillations. So that type of frequency, which after incorporating some sort of energy dissipator, will be termed as damped frequency of oscillation. While if there is no energy dissipator within the system, then the oscillations the system will exhibit is called as natural frequency of oscillation. And I told you that zeta gives you the information about damping characteristics, while omega n gives the information about system oscillations. Now let us try to find the transfer function, the closed loop transfer function of the system, which is given as C by R equal to omega n square. So this can simply be obtained either by using the reduction technique where you eliminate the closed loop, so that comes out to be equal to G over 1 plus GH. So this gives you equation 1. Now, few things to note is that a second order system exhibits a wide range of responses. So this is important. In case of first order system, we saw that the response for first order system was changing because of changing the time constant. So the only change that we observed in first order system in the responses was in the speed of response. The form of response didn't change in first order system. While in case of second order system, when you are going to change parameters, so it's not only going to change the speed of response, it will also be changing its form as well. And we'll discuss about that today. So varying parameters of first order system changes the speed of response only, whereas varying parameters of second order system changes the form of the response as well. So the speed and form both are going to change. So it's better to write here as well. So speed will also be changing. So now we'll talk about the time response of the second order system when it is subjected to step input. So let's say we have C written in terms of the transfer function multiplied by input R, and since we're talking about a step input, so R will be equal to 1 in time domain, and if you take the Laplace transform of this, you get Rs equal to 1 upon S. Now if you're going to use the partial fraction in order to factorize this, and we're going to do this in order to find out CT. So for finding CT or C in time domain, so these are few methods that you will be adopting for obtaining. What you're going to do is, if you remember the Laplace transform pairs, so what I did was I was having certain expressions on the left side of the table. So I'll show that table as well. So I guess I've drawn that table. So if you see this table, this was already been discussed in unit 1. So if you look at this table, you see that there are few expressions written on left side of F under Ft, and there are expressions written under Fs, which are nothing but the Laplace transform pairs. So I told you that it's better if you remember this table, because you will see that there are factors which are written on the right side and which can only be converted into Ft, or of these factors you can take the Laplace inverse. So your task always when you desire to obtain Laplace inverse, or for example you talk about this, so what I am trying to do now is I'm going to convert this expression into some form for which I can take Laplace inverse of. So for this I'm going to take the partial fraction of it. So I took this as 1 upon S, and the remaining term here after partial fraction. Then again I see that this term is not in any form that the Laplace inverse could be taken for. So, but what I see in the denominator is, if I convert this into some square format, for example S square plus A square. So S square plus A square form was something that comes in the umbrella of the cosine and sine transforms, Laplace transforms. So I'll try to do the same, and thus I further simplify this in order to bring this into some square form. What I did here is I added an element, an expression zeta square omega n square minus zeta square omega n square. So I did this in order to bring this into whole square form, and now further simplifying this gives me s plus 2 zeta omega n, s plus zeta omega n whole square. So if you are going to talk about this expression and zeta omega n square, so combining these three elements will give you s plus zeta omega n square. And what now I'm left with is plus omega n square minus zeta square omega n square. And if I take omega n square as common, what I'm left with is omega n square multiplied by 1 minus zeta square. So now I see that I'm going to have some terms in terms of s square plus a square. But still I have this term which is not in terms of a square, a to the whole square. So further simplifying this, and let us assume omega n 1 minus zeta square as omega d. So what I did is I assume this term, the root of this term, to be omega d. In that way I am going to replace this term by omega d square. So omega d is a new term introduced which is called as damped frequency of oscillation, and this exists because of zeta. So I told you if you're going to introduce some sort of damping elements within the system like dashpot or resistor, then what you're trying to do is you're trying to damp out the energy that the system will at some point have. So that will give rise to different frequency which will be different from natural frequency of oscillation and called as damped frequency of oscillation. Now if you remove the zeta, if you suppose you substitute zeta equal to 0, in that case omega d gets equal to omega n. What does that mean? It means that zeta can only be 0 if you somehow remove the elements which are responsible for damping, like resistor in electrical network and dashpot in mechanical system. So if you don't have any dashpot in mechanical system or resistor in electrical circuit, in that case zeta will be 0, and then you will not be having any sort of damping, and thus damped frequency of oscillation will in fact be nothing but natural frequency of oscillation. In that case the system will keep on oscillating indefinitely. Now if you're going to substitute this, what we get at the denominator is s plus zeta omega n whole square plus omega d square, and further simplifying this, we still don't have this form so that we can take Laplace inverse in cos or sine, because if you remember that for the terms cos and sine we had s square plus a square was the Laplace transform of cos at, and for sine at we had a over s square plus a square. So this comes from the Laplace transform of sine at, and this from cos at. So we see that in the numerator we have both the terms. One term is in terms of s, the other is a constant a term which comprises of zeta and omega n. So we are going to separate them out, and we wrote this. Okay, before this, so not the whole 2 zeta omega n will be separated, because we see that there is a term s plus zeta omega n. So there was one more property that we studied in Laplace domain, was if you take the Laplace transform of e raised to the power minus at ft. So this was the property that we studied there. So Laplace transform of this was equal to f s plus a. So this was the property we already studied. So we are now having the expression s plus a here, while you have s plus 2a here. So what we did is we separated s plus a here, and then we have a here. So you now have a form which is similar to cos, the Laplace transform of cos at or cos omega t, and then you again have a form here which is similar to the form sine at. But for taking the Laplace in terms of sine at, you should have these elements same. So we are having zeta omega n here and omega d here. So what now we did is we multiply and divide this by omega d, the numerator as well as denominator. Now further simplifying this, you get 1 upon s plus zeta omega n, and the same term is written here, and this can further be simplified as zeta omega n multiplied by omega d, and omega d multiplied in the denominator, and further if you take the Laplace inverse, so the zeta omega n by omega d will be taken out, and the remaining term you will be taking Laplace inverse of. So for 1 upon s, the Laplace inverse is 1. For this term you have, since you see that this is written in terms of s upon s square plus a square, and you don't have simply s here, rather s plus a term b. So you have s plus b, so which will contribute to e raised to the power minus bt, where b is zeta omega n. And then you have an expression for cos omega t. So this is e raised to the power minus at ft. The Laplace transform of this will be written in this form. Then again you have another form, e raised to the power minus at ft, the Laplace transform of which is omega d over s plus zeta omega n whole square plus omega d square. So if you take the Laplace inverse of this, you get sine omega dt e raised to the power minus zeta omega n t, and then you have a remaining term zeta omega n by omega d, which is written here. So I guess this is clear. Now, if I further simplify this, and I know that omega d can be written in terms of omega n as omega n under root 1 minus zeta square, so I cancel out omega n in the numerator and denominator, so what I'm left with is zeta upon under root 1 minus zeta square. And further simplifying this gives me e raised to the power minus zeta omega n t, and you took out the denominator out of the braces, and then what you're left with is this expression. And this can further be simplified by assuming a right angle triangle where you have angle phi, the perpendicular of which is under root 1 minus zeta square, and the base is zeta. And if you're going to evaluate the hypotenuse for it, this will, you will be having this as 1. So using this concept, we are going to now simplify and write these expressions in terms of phi. And of course, this is going to hold only for values of zeta lying between 1 and minus 1. So if you simplify this further, you write under root 1 minus zeta square using this right angle triangle. You see that under root 1 minus zeta square can be written in terms of sine phi. So sine phi is equal to under root 1 minus zeta square upon 1. So it's written here. While zeta can be written in terms of cos phi. So cos phi comes up to be equal to zeta upon 1, which is written here. Now, if you apply the concepts of the trigonometry, the properties of the trigonometric functions you learn, so this can further be simplified and written in terms of sine omega t plus phi. So since you have sine a cos b plus cos a sine b, which gives you sine a plus b. So this is the equation of the line domain output, and you have written this in a very simplified manner. If you like, you can express this in the original form by substituting omega d and phi. So since you assume phi from this triangle, what you get phi is tan inverse of under root 1 minus zeta square by zeta. And thus if you substitute each of these values, this can further be written in the original form given as follows. So this form is easy to remember. So you have Ct equal to 1 minus e raised to minus zeta omega n t upon under root 1 minus zeta square plus sine omega n t plus phi. Omega d was taken as omega n under root 1 minus zeta square, and phi is tan inverse under root 1 minus zeta square by zeta. So this form is easier to remember than this one, and thus I suggest that equation, if you are able to remember equation 2, it's good. So you can simply substitute the values of phi and omega t in order to come up with equation 3, which is the original form of the output. So this represents the output of a second order system which was subjected to a step input. So which seems to be a bit complicated, but if you try to find the values of this output for different values of zeta, then you can. So I'm going to plot those output for different values of zeta. So my first question is that how would the waveform look like if you take zeta as 0? So if you're going to substitute zeta as 0 here, what waveform Ct will be exhibiting? So this is your expression, and if you substitute zeta equal to 0, what type of waveform are you going to get? Okay, so in order to make you understand how this output is going to behave for different values of zeta, so I'll try to plot this. You can easily evaluate for zeta equal to 1 by substituting, 0. If you substitute zeta equal to 0 here, you get this as e raised to power 0, which is 1. And again, you're going to get 1 here, sine omega, this 1 minus zeta. You substitute this as 0, you get 1 omega and t, you're left with plus tan inverse of 1 upon 0, which is infinity, and this goes to 0. So now, what I'm going to do is I'm going to plot CT for different values of zeta, and I'll be choosing zeta as 0, then I'll be choosing zeta as 0.3 second value, then third value I'll be choosing it as 0.8, then I'll be choosing zeta as 2, then as 5. Then there are two more cases. In fact, these cases are something that are referred to as stable. In fact, these are stable, and the term zeta corresponding to 0 is marginally stable or critically stable. I'll be talking about these values or these ranges tomorrow in detail, but just a glimpse in how the output behaves for different values of zeta. So you'll be having a critically damped case where because zeta when taken as 0 means that the system will not be having any sort of energy dissipator, which means resistor in electrical network will be absent or dashboard in mechanical system will be absent. So we'll see how output behaves for 0. Then if you are going to have a small value of zeta, which means that we'll be providing energy dissipator having smaller values, that will give you 0.3. Then 0.8 means a larger value of dissipator yet smaller than 2. Then you have 5, which means that you are going to provide values of energy dissipator quite large. Then I'll talk about the waveform when you're going to take zeta equal to minus 0.1. Then I'll plot zeta, the waveform CT for zeta taken as minus 1.2. So these are negative values of zeta and they are unstable cases, which means that we say the system is unstable when for a bounded input or for, let's say we have provided it a step input which is not going beyond bound, which is not going beyond limits. But if you're going to get the output which goes beyond limit, so there is no extent of the boundaries of the output for a bounded input, then you say that the system has become unstable. So for zeta which taken as negative, you'll see that the waveform will become unstable and the output will not be having any limit and it will be going out of bound. So let's try to plot this using the simulation software. So I'll plot this one by one, starting from zeta equal to 0, then 0.3, then 0.8, then 2, then 5. So this is the waveform corresponding to zeta equal to, let me enlarge this. So this corresponds to waveform when zeta is taken as 0. So we see that the oscillations are undamped and the limit you can see of the oscillation lies between 0 and 2. So this is pure sinusoid without any sort of damping. And this is what happens when you don't have any energy dissipator within the system. Now if you provide energy dissipator having a smaller value, you have this type of waveform which is damped. So this waveform corresponds to zeta equal to 0.3. And the next upcoming waveform will be corresponding to zeta taken as 0.8. So you will be increasing the value of the energy dissipator. So this is the waveform that corresponds to zeta equal to 0.3. And now we'll draw zeta 0.8. So this is the waveform for in black. So this is for zeta taken as 0.8. So we see that when we are increasing the value of zeta, one thing is that the waveform is going to get slow. So the response is slower and it reaches the desired value late. While zeta taken is smaller, the desired value is achieved early. And moreover, apart from the response being slow for higher values of zeta, we see that for smaller values of zeta, there are overshoots and undershoots. So since you provided the system with an input R, which was taken as 1 as step input. Now this is the output response for zeta taken as 2. So for smaller values of zeta, we see that there are oscillations, and R, since it was taken as 1, as an input was given to the system as 1, the output is also 1, but having waveforms which are different in nature, the form of waveform is different because of different values of zeta. And we see that on increasing the value of zeta, the oscillations die out or they decreases. Now this waveform corresponds to zeta taken as 5. So the response is pretty slower and it will reach the steady state much later than all others. So this means that you provide the system with a larger value of energy dissipator. So now what value of zeta is to be chosen for system depends upon what application you're talking about. For example, if I talk about a so can anyone give me an example of second order system used in real life? Where in your daily usage do you have seen second order systems? Here comes the response of CT when zeta is taken as negative. So you can see that this is unstable. I've taken zeta minus 0.1 in this case. So you will observe that the CT will keep on increasing indefinitely, and thus you don't have any bound in the output. It will keep on increasing, and moreover you see that this has both type of responses, sinusoid as well as exponential. So sinusoid is clear, but if you look at the edges of this waveform, you'll see that it is exponentially rising. So this type of waveform is unstable and is obtained by taking zeta negative close to minus 0.1. Now here comes the waveform for zeta taken as minus 1.2. So now we see that there is no sinusoidal effect on the waveform. The whole waveform seems to be exponentially growing, and if you see the values, you see that the values is increasing at every step. So we now approach 10 raised to the power 8 and will keep on increasing. So this is an unstable case. So because we are able to simulate it, that is why we are reaching these large values. But in physical sense, you cannot achieve these large values because there must be some sort of saturation within the system or breakdown that will occur in the system if you go to very large extent of output. So if you talk about, let's say, CT in terms of in physical sense, let's say CT is the displacement of mass. So displacement of mass indefinitely cannot be possible because you are bound to have breakdown within the system if you go beyond certain limit in physical systems or electrical systems. So zeta negative are unstable. So my question now is this would be, can you give a physical example of second order system in your real life, in your practical life, where you might be using it daily? I need a real example that you are using daily, in your day-to-day life. A second order example of a second order system.